This is a problem session in which we will deal with some problems based on the material we saw in the last week. We'll begin by considering a key result which we have used multiple times, which was given to you as an exercise. The problem is about proving that the arc length of the concatenation of two curves is the sum of the arc lengths. Let me write down the problem and then let's prove it. So the problem 1 is the following. Let gamma 1 be a curve from the interval AB and gamma 2 be a curve from CD into C be such that the terminal point of gamma 1, that means gamma 1 of B, this is equal to the initial point of gamma 2. It means gamma 1 of B is equal to gamma 2 of C, and hence we can talk about concatenation of gamma 1 and gamma 2. Then the arc length of gamma 1 plus gamma 2, the concatenation of gamma 1 and gamma 2, that is the sum of the arc length of gamma 1 and the arc length of gamma 2. Let's give a concrete proof of this statement. The first observation is that if you look at a continuous reparameterization of a given curve, then the reparameterized curve also will have the same arc length. This was given to you as an exercise. I will request you to sit down and give a proof of it if you have not already given one. Assuming this particular exercise, we may assume, without loss of generality, that B is equal to C. That means the end point of the interval AB and the initial point of the interval CD are the same. We can assume without loss of generality by doing a translation of the interval CD to the interval B comma E, where E will turn out to be a D minus C plus B, something like that. We can get hold of the right reparameterization where the interval starts from the point B. So we will assume without loss of generality that B is equal to C. And by the observation that reparameterization does not change the arc length of our given curve, we will still be proving this result for good. We will assume that B is equal to C, and we will show that the arc length of gamma 1 plus gamma 2 and the sum of the arc length of gamma 1 and the arc length of gamma 2, they are arbitrarily close. That will be the strategy of the proof. So let epsilon positive be given, and we partition the interval A comma D, which is now the domain of definition of gamma 1 plus gamma 2. Remember that B is assumed to be equal to C. Let epsilon positive be given and let P given by A equal to T0 less than T1 less than all the way up to say Tk, which is equal to C, which is the same as B. This is less than Tk plus 1 less than all the way up to Tn equal to B. Let this be a partition, let P be a partition of A comma D, which remember is the union of A comma B union B comma D, which respectively is the domain of definition of gamma 1 and gamma 2. We have partition of this interval such that, let's now use the definition of the arc length of a curve. The arc length of gamma 1 plus gamma 2, which is the supremum over all numbers of the type which I am writing down here. Gamma 1 plus gamma 2 of Tj, the absolute value of this, minus gamma 1 plus gamma 2 of Tj minus 1, where j is going from 1 all the way up to n. So this is precisely what we have to consider to get hold of the arc length of a given curve. We look at the supremum of such numbers over all partitions. And let's pick one such partition which satisfies this condition, which that gamma 1 plus gamma 2 arc length is at a distance of less than epsilon by 3. Not just that, we can do more. We can demand that this satisfies this condition as well. Let me put and such that the arc length of gamma 1 minus gamma 1 of Tj minus gamma 1 of Tj minus 1. Now let me be a bit careful with the indices. This is going to go from 1 to k. Remember that gamma 1 is defined on the interval AB. And if you look at the partition here, which I am now underlining, up till k, tk, this is going to be a partition of AB. Right, so this is again less than epsilon by 3. We are not done, and such that the arc length of gamma 2 is also similarly at a distance of, we'll worry about the indices after we write it down, gamma 2 of Tj minus 1, where this j now goes from k plus 1 to n, and this is again less than epsilon by 3. What is the first question that we will be asking here? Can we have one such partition at all? The answer is yes, because there can be a partition which satisfies this condition of AB, of AD. There can be a partition of this which satisfies this condition of AB. There will be a partition of B comma D which satisfies the third condition. Now we go down to a common refinement. Now notice that the partition of AB and BD together will give you a partition of AD, and by going down to the common refinement of the two partitions of AD, we will be able to ensure that these conditions, all these conditions are satisfied. So this is something which we can certainly ensure, and once we do that, we are in good shape, because then let's look at the absolute value of the arc length of gamma 1 plus gamma 2 minus the arc length of gamma 1 plus the arc length of gamma 2, so that there is no confusion. So this is less than or equal to the absolute value of the arc length of gamma 1 plus gamma 2 minus summation j is equal to 1 to n gamma 1 plus gamma 2 of Tj minus gamma 1 plus gamma 2 of Tj minus 1. Remember that whenever I write gamma 1 plus gamma 2 here, it's still a curve. Even though there is the plus notation, the concatenation is the exact same way we have defined it during the lectures. And the second term will be, I'll just rearrange the terms and write it this way: the arc length of gamma 1 plus gamma 2 minus summation j is equal to 1 to n gamma 1 plus gamma 2 of Tj minus gamma 1 plus gamma 2 of Tj minus 1. The first term we have already ensured. This, which I am now writing in green, this is strictly less than epsilon by 3. That's something by choice we already have, by the choice of the partition. And the second term, so this is going to be less than epsilon by 3 plus, let's worry about the second term. I will do a further triangle inequality here and write it in this manner: j is equal to 1 to k. What is gamma 1 plus gamma 2 of Tj when j is less than or equal to k? That's going to be equal to gamma 1 of Tj by the definition of the concatenation. So let me write that down. This is basically the same as gamma 1 plus gamma 2 of Tj when j is going from 1 to k, minus gamma 1 of Tj minus 1. And the second term would be, let's see, where j is now going from k plus 1 to n. I'm just splitting that sum from j equal to 1 to n to j equal to 1 to k and j equal to k plus 1 to n. And this is just gamma 2 of Tj minus gamma 2 of Tj minus 1 by the very definition of concatenation. So we are able to split the term which I am now underlining in green as this less than or equal to this plus this by the triangle inequality. Right, now how did we pick the partition P? We picked it in such a manner that the arc length of gamma 1 is epsilon by 3 close to this sum. So this is again less than epsilon by 3 plus epsilon by 3, and similarly the arc length of gamma 2 is also less than epsilon by 3 distance from the sum written there. and we get that this is entirely less than equal to epsilon. So what we have established is that the arc length of gamma 1 plus gamma 2 and the arc length of gamma 1 plus arc length of gamma 2, they are epsilon close for every epsilon positive. Since epsilon positive epsilon that was chosen was arbitrary, we have the arc length of gamma 1 plus gamma 2 is equal to the arc length of gamma 1 plus the arc length of gamma 2. And that solves the result. As a continuation, let's now prove one more result about arc length, about continuity property of the arc length. We already have seen that the arc length is monotonically increasing number. May not be strictly increasing, but it's certainly not decreasing. This problem tells us that the arc length is actually a continuous function. Let me make it precise. Let gamma from AB into C be a curve. So remember that a curve means a continuous map from AB into C. Then define the L, function L, which is representative of the length, arc length rather, from AB into R be given by, then define L to be L of t is equal to, defined to be the arc length of gamma restricted to a comma t. Then the problem tells us that L is a continuous function. And L is a continuous function. We will show that L is left continuous, and if we show left continuity, that is enough, because then we can consider minus of gamma, and the left continuity of the length function corresponding to minus of gamma will give us the right continuity of the function L corresponding to gamma. So I'll just write that down. Given t in AB, we shall prove that gamma is left continuous, not gamma, L is left continuous. Gamma is already continuous. This is enough since right continuity follows by considering the length corresponding to minus of gamma, the reversal of gamma. Remember that reversal of gamma will be from minus b minus a into c. So I'll leave it as an exercise for you to sit down and really check that left continuity here and the right continuity there are the same. Let's now prove the left continuity of the function L. We will show that given an epsilon positive, there exists some delta such that if t prime is in t minus delta to t, then L of t minus L of t prime is less than epsilon. That will establish the left continuity. So let epsilon positive be given. Now notice that gamma is a function which is continuous on a compact interval AB, and in particular it is uniformly continuous as well. So given epsilon positive, since L, or rather gamma, is uniformly continuous on the compact interval AB, there exists some delta prime such that the absolute value of gamma s minus gamma of t is less than epsilon by 2 whenever the distance of t and s is less than delta prime. Now let's use the definition of the arc length of gamma restricted to a comma t and get hold of a partition which is epsilon by 2 close to the arc length. Let p equal to a equal to t0 less than t1 less than all the way up to tn equal to t. Okay, so is it t that we picked? Yeah, we have picked a t here. So it's just the same t that's being considered here, tn be equal to t, such that if you look at the arc length of gamma restricted to a comma t, this is what we are interested in approximating. This arc length, this is epsilon by 2 close to gamma of tj minus gamma of tj minus 1, where j is going from 1 to n. Now this is less than epsilon by 2. Now let delta be less than the minimum of delta prime. Delta prime is obtained by continuing the uniform continuity, and tn minus 1. Let's consider the last part of the partition which we have just picked and look at the distance of tn and tn minus 1. Let's pick delta which is less than that. The claim is that this delta will do. So let t prime and t prime be in t minus delta to t. And let's see what happens. By considering the refinement, of the partition we have just picked, a equal to t0 less than t1 less than tn now is going to be equal to tn minus, till tn minus 1 there is no change. At tn, however, we will add the point t prime and tn plus 1 is going to be equal to t. So suppose we go down to a further refinement. By triangle inequality, we will have gamma restricted to a comma t, this minus the absolute value of gamma of tj minus gamma of tj minus 1. This is going to be again less than epsilon by 2, because when by triangle inequality we are going only closer to the real arc length that you should sit down and think about. We still have this inequality. Now we will use the previous problem to write gamma restricted to AT. The arc length of this is the same as the arc length of gamma restricted to AT prime, and then the arc length of gamma restricted to T prime comma T. And yeah, so this follows, this is equal by the previous expression, previous problem. And further we will split this into 2. J is equal to 1 to, oh, I was a bit careless, this should be n plus 1 now, because we have added a new point in the partition. Now this is going to be from j equal to 1 to n of gamma of tj minus gamma of tj minus 1. Minus, there will be one more term which is gamma of tn plus 1 minus gamma of tn, which is basically gamma of t minus gamma of t prime. So notice that I have just rewritten the expression above. So this expression is the same as this expression. There is no change. I just rewritten it, and we know that this is less than epsilon by 2. Now let's regroup it. Then we have the arc length of gamma restricted to AT prime minus the sum of gamma of Tj minus gamma of Tj minus 1, where j is going from 1 to n now, plus gamma restricted to Tt prime, the arc length of that, minus absolute value of gamma of t minus gamma of t prime. This is less than epsilon by 2. We have done nothing other than regrouping our terms here. no extra thing has been done. Yes, and we will see that now the arc length of gamma restricted to t prime comma t, this minus the absolute value of gamma of t minus gamma of t prime, this is less than epsilon by 2 minus, well, let me write this to be equal to c, where this is equal to c, where c is positive. Why is that the case? Because the arc length is the supremum over all such numbers. So in particular, this number is greater than the sum that is written to the right, and hence the difference is going to be positive. So we have c is positive, and hence this is still less than epsilon by 2. We can rewrite now what the arc length of gamma restricted to t prime comma t will be. That's going to be less than epsilon by 2 plus the absolute value of gamma of t minus gamma of t prime. But how was t prime picked? Let's go up and check how t prime was picked. T prime was picked in the interval t minus delta to t. Delta was less than the minimum of delta prime and mod of tn minus 1. In particular, it's less than delta prime. And by the uniform continuity of gamma, the number gamma of t minus gamma of t prime will be less than epsilon by 2. So this will be less than epsilon by 2, which is equal to epsilon. Therefore, gamma restricted to t prime comma t, the arc length of this is less than epsilon, whenever t prime is in the delta neighborhood to the left of t. We are not still completely done, we are still one step away. We should note here that this is exactly equal to the arc length of gamma restricted to at minus the arc length of gamma restricted to at prime. This is precisely what we have, because this follows by the first problem, and this is exactly equal to i.e. L of t minus L of t prime is less than epsilon. That's precisely what we had set out to do. So we have established that the function L is a continuous function. We have seen how to compute the integral of a function defined on a curve. Let's now do some explicit computations of such an integral. I will not do all the computations. I'll show you how to do the computations in the setting we have discussed, and leave you with a solution at a stage where it can be taken forward by you by using elementary calculus. So we will consider the following function. Let f be the function defined to be equal to 1 by z square minus 1. Notice that this is a rational function which is defined away from 1 and minus 1. It's holomorphic away from 1 and minus 1. Anyway, we just need continuity on a curve. So what is the curve we are considering? And gamma from 0 to pi into c be the curve given by gamma of t is equal to 2 times e to the power it. So what is the curve gamma here? Gamma is going to be the circle of radius 2 around the origin. So let this be 1, this be I, this be 2i, this is minus 2, okay, this is minus 1, 1, 2, minus I, minus 2i. So this is a circle which I hope I draw it properly. Yeah, this was intended to be a circle, but that's okay. So the green thing that I have drawn is the circle of radius 2, and our goal is to integrate. So what is the goal? Compute integral of f of z dz over gamma. This is what we are going to do. Now the good thing is that the curve that we are considering is continuously differentiable. In fact, it's smooth. So we will use that aspect of the curve to use the change of variables formula. So let's look at the solution. Let's see what it is. By the change of variables, we'll do the computation explicitly. By the change of variables formula. Oh, before we apply the change of variables formula, let's look at what the function is. Since f of z is equal to 1 by z square minus 1, and by writing it in terms of partial fractions, we can write that this is equal to half of 1 by z minus 1 minus half of 1 by z plus 1. So z plus 1 minus z minus 1 will give you 2z, the 2's will cancel off, this is 2 rather, 2's will cancel off, and we have 1 by z minus 1 into z plus 1, which is z square plus 1. So this is precisely what we have, the function that we have. And if you look at integral of f of z dz over gamma, this is going to be equal to the integral of half of 1 by z minus 1 over gamma minus the half of the integral of 1 by z plus 1 over gamma. We will compute these two terms explicitly. We will do it by using the change of variables that we just discussed, and this is equal to half of gamma. What is the change of variables? Integral of f of z dz over gamma will be a to b f of gamma of t, gamma prime t dt. So that's going to be half of 0 to 2 pi, that's where our curve gamma is defined, gamma prime t. So gamma, let me recall, gamma of t, that's going to be 2 e to the power it. Gamma prime t is going to be equal to 2I e to the power it dt by 2 e to the power it minus 1 plus, or rather minus, half of 2I e to the power it dt by 2 e to the power it plus 1. So this is precisely what we will have to compute. I'll just show you how the first term can be computed and leave the second term to you. That's going to be quite similar. Even the first term, I'll just show you what we are exactly dealing with. Consider half integral 0 to 2 pi 2 I e to the power it dt by 2 e to the power it minus 1. We will multiply by the complex conjugate of the denominator, and we will have, so the 2's will cancel off, I will come out, and that will be integral I times the integral 0 to 2 pi of e to the power it to e to the power minus it minus 1 by the absolute value of 2 e to the power it minus 1 square dt. Now let's write this. So this is going to be equal to 2 minus e to the power it, and we will be getting I times 0 to 2 pi 2 minus cos t plus, or rather minus I times sin t by, this is going to be equal to 2 cos t minus 1 the whole square plus 2 sin t the whole square. And a computation there will tell us that this is equal to 5 minus 4 cos t dt. Now let's group the terms. This is equal to integral 0 to 2 pi sin t by 5 minus 4 cos t dt plus I times integral 0 to 2 pi 2 minus cos t by 5 minus 4 cos t dt. Now we are in good shape. because we just have to compute two integrals of real valued functions. Now we are in the setup of real analysis, where you can sit down and compute these integrals explicitly from your high school calculus practice. You can check that this is going to be 0. There's an explicit antiderivative which you can get hold of. I will leave it to you to compute this complicated integral in the brackets here. Computing the integral here, if I have not made any mistake earlier, it should turn out to be equal to pi times I. And therefore, we will get that this term is equal to pi times I, this entire term inside the bracket. A very similar computation, if you sit and do, you will see that this will also turn out to be equal to pi times I, and we will end up with, so let me just note that down, by a similar computation, so this term can be computed by that Weierstrass substitution by looking at x is equal to tan of t by 2, I guess. Yeah, anyway, I'll leave that to you. By a similar computation, we also have half of integral of 1 by z plus 1 dz over gamma is also equal to pi times I. And therefore, integral of 1 by z square minus 1 dz over gamma will be equal to pi times I minus pi times I, which is equal to 0. We will see later that this can be computed more easily by developing some more theory in the next few weeks. We'll come to that. Right now we have explicitly computed the integral of 1 by z square minus 1 over this curve gamma. It will be a good exercise for you to sit and work out a variant by changing our curve gamma. Let gamma be the curve given by 1 plus e to the power it. Just changing the curve so that this is now a circle centered at 1 and with a radius equal to 1. So the curve now is going to be something like this. It's a circle centered at 1 of radius 1. Remember that 1 by z square minus 1 had problems at minus 1 and 1, but now minus 1 is outside this circle, it's not in the interior. We'll discuss all these things in great detail, and let me just tell you that when you compute 1 by z square minus 1 over that curve, we will still be able to write it in this manner. Now what will happen is at this particular integral, this is going to vanish, and this is what will survive, and the value will again turn out to be equal to pi times I. That's something which I will leave it to you to sit down and check. So this is an exercise within the problem session. So let me just put it that way. Compute the integral of 1 by z square minus 1 over gamma. The next couple of problems deals with the fundamental theorem of calculus. Let me write it down for you. What is this problem? This is problem 4, I guess. Prove that the function f of z equal to 1 by z does not have an antiderivative in c minus 0. Omega here is c minus 0. So this problem will turn out to be a direct application of the first fundamental theorem of calculus. If you recall, the first fundamental theorem of calculus said the following. Suppose f is a function which is continuous and defined in omega, and suppose capital F is an antiderivative of small f, that means capital F prime is equal to small f, and suppose there is a curve gamma, and if we integrate small f over gamma, then we have the integral is equal to capital F of z1 minus capital F of z0, where z1 is the terminal point and z0 is the initial point. We will show that the antiderivative, if it exists in this problem, it does not satisfy the fundamental theorem of calculus, and thereby we will be able to conclude that it does not have an antiderivative. And in order to do that, let's consider a closed curve in C minus 0. Let's give a proof. Let us consider the circle of the unit circle, the circle of radius 1 around 0. Consider gamma of t to be equal to e to the power I t, gamma on 0 to 2 pi. So this is going to be the unit circle of radius 1. Its starting point is the complex number 1 and its end point is also the complex number 1. If our function f had an antiderivative, if f of z had an antiderivative in C minus 0, notice that our unit circle does not pass through the origin and therefore it is a curve in C minus 0. So if f of z had an antiderivative in C minus 0, then say capital F, then integral of f of z dz over gamma, that's just going to be equal to f of the end point, which is 1, minus f of the initial point, which is also 1, and that will turn out to be equal to 0. So basically the integral of such functions over closed curves is going to be 0. But let's now do one thing. Let's sit and compute explicitly what the integral of f of z over gamma is. Let's compute integral f of z dz over gamma. And in order to do that, we will use the change of variable. Gamma is a very nice curve. It's not some arbitrary rectifiable curve. Indeed, it is a rectifiable curve, but it's much more. It's actually a smooth function. It's continuously differentiable with no singularities. So gamma of t, so what we are doing can be done for continuously differentiable functions. It's e to the power I t, and by using the change of variables, integral of 1 by z dz over gamma, this is going to be equal to I e to the power I t dt, that is what gamma prime t dt is, by e to the power I t, that is f of gamma of t, and the integral is from 0 to 2 pi. And what we end up is I times the integral from 0 to 2 pi of dt, which is equal to 2 pi I, which is certainly not equal to 0. Therefore, the function f of z equal to 1 by z does not have an antiderivative. We will come back to this question of when we can talk about the existence of an antiderivative of 1 by z later, but on C minus 0 we have just established that we do not have an antiderivative. So there are domains where we cannot talk about the antiderivative of f. Let us conclude this problem session by proving the integration by parts for holomorphic functions. Let me write down the problem and let's prove it. Let omega contained in C be an open subset of the complex plane, and f and g be two functions which are holomorphic on omega. Omega to C be holomorphic. Let gamma from AB into omega be some rectifiable curve, be a rectifiable curve. Then integral f of z g prime of z dz over gamma, this is equal to f of z1 g of z1 minus f of z naught g of z naught minus the integral over gamma f prime of z g of z dz, where z0 and z1 respectively are the initial and the terminal points of gamma, where z0 and z1 are respectively the initial and terminal points of gamma. The expression written here is what's popularly called as the integration by parts. The proof is actually quite straightforward. It's a direct consequence of the fundamental theorem of calculus. Suppose we look at the derivative of f and g. So let capital F of z be given by f of z g of z derivative of this, so d by dz of this rather. Let me just put a prime here to denote that we are looking at the derivative of f of z times g of z. Then what is the fundamental theorem of calculus telling us? By the fundamental theorem of calculus, integral of f of z dz over gamma, that is going to be equal to f of z1 g of z1 minus f of z0 g of z0. But we also know what f is. We know that f of z is f of z times g of z prime. By the product rule tells us that capital F of z is equal to f prime of z times g of z plus f of z times g prime of z, where f prime and g prime respectively are the derivatives of f and g. Remember that we have started off with holomorphic functions f and g, so all this makes sense. And by the properties of the integral we have discussed earlier, integral f over gamma, integral of f of z dz over gamma, this is equal to the integral of f prime of z g of z dz plus the integral over gamma of f of z g prime of z dz. And that's precisely what we had set out to prove, that both these numbers are equal. And with that we get a very straightforward proof of the integration by parts. Alright, let me stop here.